The defining tension of modern civil engineering occurs at the precise moment a structure collides with the earth. A skyscraper is a rigidly engineered geometry of steel and concrete, but it must rest entirely upon highly variable, non-homogeneous geological strata. If an engineer fails to map the mechanics of this specific subterranean interface, the structure's downward force will exceed the soil's shear strength. The soil will undergo plastic deformation, yielding permanently under the weight. This causes excessive differential settlement across the foundation, tearing the rigid structural frame apart and inevitably leading to catastrophic failure. If you want to understand the exact mechanics keeping our city standing, hit the like button, subscribe to Insight Engine, and let's dig into the math. Foundation design is a strictly deterministic, sequential process. It requires translating raw, chaotic subterranean data into highly specific mathematical models, and then binding those models to rigorous legal construction codes. To safely transfer thousands of tons of structural load into the ground, engineers employ two overarching mechanical strategies. They either spread the weight widely over a large surface area near the ground level, or they bypass weak surface soil entirely to anchor the building deep underground. Human intuition is useless for determining which method to use. You cannot look at a patch of dirt and guess its bearing capacity. Rigorous physical site investigation and mathematical prediction are the only defenses we have against structural collapse. The absolute prerequisite for any structural design is a physical site investigation. Before a single footing is sized, heavy drill rigs are mobilized to the site footprint to extract continuous physical soil samples from deep underground. One of the primary tools used is the Standard Penetration Test, or SPT. This involves driving a heavy steel sampling tube into the ground with a standardized drop weight. The number of blows required to drive the tube a specific distance generates an N value, a critical metric that reveals the exact shear strength and relative density of the specific soil layer. For an even more detailed picture, engineers use the Cone Penetration Test, or CPT. By pushing an instrumented cone steadily into the ground, the CPT measures continuous tip resistance and side friction, mapping a seamless, high-resolution stratigraphic profile of the subsurface. This bore log aggregates the test results. It combines CPT stratigraphy, SPT N values, and groundwater elevation into a comprehensive vertical map of the Earth. This translates into the most critical metric, safe allowable bearing capacity. This is the maximum pressure the ground can safely sustain before failing. You cannot calculate the size of a concrete footing or the depth of a pile without first quantifying these physical limits. The entire mathematical framework of civil engineering relies entirely on the accuracy of this subterranean data. When the near-surface soil possesses a shear strength that comfortably exceeds the downward stress of the proposed building, engineers deploy shallow foundations. Terzagh's ultimate bearing capacity equation sizes shallow foundations to prevent soil failure. The first term, C, represents soil cohesion resisting outward force. Depth, D, uses backfill weight to press down and lock soil in place. Width, B, geometrically spreads the load, lowering contact pressure. High winds and seismic activity generate lateral forces that result in violent overturning moments. These dynamics shift the stress away from simple downward gravity loads. To manage this, engineers use the P over A plus or minus M over S formula. P represents the total vertical load, A is the footing's base area, M is the overturning moment, and S is the section modulus. This diagram illustrates what happens during a wind or seismic event. The overturning moment generates a tilted, triangular pressure distribution. Instead of pushing down evenly, the building focuses an intense, concentrated spike of stress onto a single edge of the underlying soil. Engineering codes enforce a strict requirement here. The entire base of the foundation must remain in compression. If the lateral force is too high, the footing experiences tension, meaning the structure is literally attempting to lift off the ground and tilt. Shallow foundation design relies on geometric surface area manipulation. The goal is to calibrate the width and depth of the concrete pad so that even under the worst-case dynamic loads, the localized stress stays safely below the soil's critical failure threshold. When surface soils are highly compressible, or when dealing with the massive, concentrated structural loads of a high-rise, shallow dispersion is no longer viable. The stress will simply crush the surface layers. A pile foundation's mechanical purpose is bypassing incompetent surface strata to transfer extreme loads directly down into dense, highly competent geological layers, like solid bedrock. The pile capacity formula shows a two-part load transfer mechanism. End-bearing capacity, QP, is the hard stratum's compressive resistance pushing against the pile tip.
Skin friction capacity, QS, is the cumulative shear resistance developed along the lateral surface interacting with surrounding soil. While friction piles are highly effective in uniform soils, specific regional geotechnical hazards require entirely different mechanical solutions. In the Indian subcontinent, engineers frequently encounter highly expansive black cotton soils. These cohesive, clay-rich soils are volumetrically unstable. During monsoon season, they absorb water and expand forcefully. In dry summer months, they shrink and form deep fissures. This relentless wet and dry cycle creates massive seasonal uplift pressures, capable of ripping standard friction piles straight out of the ground. To counteract this, the Indian Standard Code IS 2911 mandates a highly specialized mechanical solution, the Underreamed pile. This cross-section illustrates the exact geometry required. An underreamed pile features mechanically formed widened bulbs cut directly into the base of the concrete shaft. By code, the diameter of these bulbs is exactly 2.5 times the width of the main stem. These widened bulbs are positioned deep underground, acting as permanent physical anchors. By locking the pile firmly below the active moisture zone, the foundation resists the violent seasonal swelling and shrinkage of the upper soil layers. Deep foundations act as complex friction engines, specifically calibrated to neutralize aggressive subterranean hazards. Standard physics formulas assume perfect materials and ignore the necessary safety margins required to account for real-world geological uncertainty. This is where international building codes step in. Documents like the American ACI 318, the European EN 1997, and the Indian IS 1904 mandate deterministic safety protocols and exact structural detailing. These codes operate on divergent philosophies. The American framework leans heavily into highly prescriptive, formulaic mandates for minimum thickness and steel spacing. The European paradigm relies on a performance-based limit state methodology, applying probabilistic partial factors to account for statistical reliability. Both systems aggressively regulate critical structural junctions, particularly the pile cap. A pile cap is a massive concrete transfer node that connects the slender, heavily loaded columns of the superstructure above to the deep foundation piles below. At this junction, the primary threat is a catastrophic failure mechanism known as two-way punching shear. This wireframe diagram shows the exact mechanics of punching shear. The extreme concentrated point load from the column does not just bend the concrete, it attempts to literally punch a cone-shaped hole straight through the footing slab and into the earth. To counteract this, codes like ACI 318 dictate strict volumetric limits. They require a minimum effective depth for the bottom reinforcement, typically at least 12 inches for pile caps, ensuring sufficient concrete mass to anchor the reinforcing steel and physically resist the immense localized shear stress. This regulatory matrix is essential. It translates theoretical soil mechanics into rigid, legally binding physical parameters, guaranteeing public safety by removing the margin for individual calculation error. A mathematically perfect, code-compliant design model remains vulnerable if the physical construction execution is compromised. The transition from paper to dirt requires constant technical oversight. During the excavation phase, engineers must maintain rigid field controls. If the site has a high groundwater table, aggressive dewatering techniques are required to pump water out of the trench, preventing the surrounding soil walls from losing cohesion and instantly collapsing. When installing deep foundations, strict pile-driving verticality tolerances are monitored continuously. A pile driven even slightly off plumb will induce massive unintended bending moments. Simultaneously, the heavy steel reinforcement cages must be placed with absolute precision before the concrete is poured, to ensure the designed shear capacities are actually met. To physically prove that the constructed foundation matches the theoretical mathematical assumptions,
engineers conduct empirical field testing using massive hydraulic jacks and reaction beams. They perform static load tests, applying extreme downward pressure to a test pile to confirm its actual yield point in the soil. Today, modern geotechnical engineering integrates site data, complex mathematics, and strict legal codes using advanced finite element analysis software like Plaxis 3D. This allows engineers to model highly complex hybrid systems, such as piled rafts, visualizing exact soil structure interactions before ground is even broken. The engineering workflow translates chaotic physical data into mathematical stress limits, enforces those limits through international codes, and realizes them through heavy-duty physical construction. If you found this breakdown of geotechnical mechanics valuable, hit the like button, subscribe to the channel, and follow Insight Engine for more professional engineering deep dives.